Regression. In classification, given an input, the output that is generated is Boolean. It is a yes or no answer. When the output is a numeric value, what we would like to learn is not a class. C of x belongs to 0 or 1 but is a numeric function. In machine learning, the function is not known, but we have a training set of examples drawn from it is here as follows, where x equals to x to the power t, comma r to the power t in the limit of t n where t is equals to 1. Where rt belongs to r, if there is no noise, the task is interpolation. We would like to find the function fx that passes through this point such that we have rt equals to f of xt. In regression, there is noise added to the output of the unknown function rt equals to f of x to the power t plus epsilon. We would like to approximate the output by our model gx. The empirical error on the training set x is as follows, as a given formula or equation here you can see. Its minimum point can be calculated by taking partial derivatives of E with respect to W1 and W0, setting them equal to 0, and solving for the two unknowns W1 and W0 is as the following equation or the formula over here. This figure here depicts linear second order and sixth order polynomials are fitted to the same set of points. The highest order gives a perfect fit, but given this much data, it is very unlikely that the real curve is so shaped. The second order seems better than the linear fit in capturing the trend in the training data. You can see the single input linear model, this one, is gx equals to w1x plus w0, and higher order function of the input is gx equals to w2x to the power 2 plus w1x plus w0. Model selection and generalization. Here as follows. Learning is an ill-posed problem. The data is not sufficient to find a unique solution. The need for inductive bias assumption about age and generalization is how well a model performs on new data. Overfitting says where H is more complex than C or F. Underfitting says H is less complex than C or F. Triple trade-off. Can see there is a trade-off between three factors: complexity of H, CH, training set size N, generalization error E, or new data. As the amount of training data increases, the generalization error decreases. As the complexity of the model class H increases, the generalization error decreases first and then starts to increase. Cross validation. To estimate generalization error, we need data unseen during training. We split the data as follows: training set 50%, validation set 25%, test set 25%, and then resampling when there is few data. Dimension of a supervised learner model, where G of is the model, X is the input, and theta are the parameters. Loss function. To compute the difference between the desired output and our approximation to it, given the current value of parameters theta, the approximation error or loss is the sum of the losses over the individual instances. This is the equation of loss function. Optimization procedure, where argmin returns the argument that minimizes. This is the optimization procedure. Thank you.